In this module, we are going to look at the stoichiometry involving chemical equations, specifically looking at mole-to-mole calculations. By the end of this module, you should be able to calculate the amount of a reactant or product based on the given quantity of another substance in the reaction. So stoichiometry is the quantitative study of reactants and products in a chemical reaction. Some of the questions we can answer by using stoichiometry are: how much hydrogen gas is produced when 1 kilogram of sodium metal reacts with water? Or, how much iron is needed to produce 34.5 grams of iron oxide? Many questions like this can be answered using stoichiometry. Now, these questions involve masses of substances, either in grams or kilograms, and we will get to several examples using those units. But first, we need to start by looking at the molar relationships between the amounts of two substances in a chemical equation. To do these calculations, we're going to use something known as the mole method. This is where we use stoichiometric coefficients from a chemical equation as the number of moles of each substance. This allows us to write relationships between any two substances in the equation. When we started talking about balancing equation, we first looked at the number of molecules or the number of atoms. Now we're going to look at it in terms of moles. For example, for our equation here, we have 4 moles of aluminum reacting with 3 moles of oxygen to form 2 moles of aluminum oxide. I'm going to be able to write relationships between any two of these substances in order to understand the amount of that substance relative to the amount of a given quantity. This map of stoichiometric processes can help us solve our problems. Note that we start with a known amount of a substance and we go to an unknown. There's no distinction between whether we're talking about a reactant or a product. As long as we have a known and an unknown and a balanced chemical equation, we can set up ratios between any two substances. They can be 2 reactants, 2 products, or 1 reactant and 1 product. It simply depends on what information we're given and what information we're looking for. Now we notice that there are many other units on this particular diagram that give us a map of how we can get from one to the other. However, our initial focus will be on the middle of this diagram, which is just dealing with moles. So let's focus in on moles of A to moles of B. Notice in the middle that our relationship is determined by the coefficients from our balanced equation. Without a balanced equation, we cannot understand the relationship between any two substances. The key for many of our calculations will always be converting to moles, using the ratio, and then converting to finding the moles of our unknown. Again, it doesn't matter whether we're looking at reactants or products, as long as we have a balanced chemical equation to determine the relationship between our known substance and our unknown substance. So let's look at an overview of what we call the mole method. First, we need to write correct formulas for all reactants and products. Then, we need to balance the resulting equation. If the equation is given, we should always check that we have a balanced chemical equation and that all elements are balanced. Next, we're going to calculate the quantities of any known amounts into units of moles. This will be represented by our moles of A in our diagram. Then, we can use coefficients to calculate the number of moles of the unknown quantity. This is our relationship between moles of A to moles of B, regardless of where each of those substances is found in the equation. Next, we will use molar amounts to convert to units of the unknown quantity. So initially we're starting with a mole-to-mole relationship, but eventually we're going to want to convert those moles of our product or moles of our unknown into grams or liters or atoms, and so we need to finish the problem by doing that. The last step, which is probably one of the most important steps, is: does our answer make sense? Is our answer reasonable? If we start out with milligrams of a reactant, it is highly unlikely that we're going to end up with kilograms of a product. So that way we need to be able to decide, does our answer look reasonable? Does our answer make sense? You may not be able to distinguish between whether it's 42 or 47 just by guesstimating an answer, but you should know if it's a difference between, say, 40 grams and 800 grams. So look at the values you're given and see if your answer is reasonable. Now we're able to add another tool to our toolbox for looking at relationships and conversion factors. We've seen many relationships and conversion factors in going from things such as grams to moles, moles to the number of a substance, between grams and milliliters, using our metric prefixes, using our subscripts to get between molecules and atoms, and now we can use our coefficients from our balanced equation to get the relationship between moles of A and moles of B. Let's look at some of the examples of relationships we can get from our balanced chemical equation. For every 1 mole of propane, we need to have 5 moles of O2 because our relationship in the balanced equation is 1 mole of propane to 5 moles of oxygen. For every 1 mole of propane, we can generate 3 moles of CO2 and 4 moles of water. So these stoichiometric relationships give us the relationship between the amount of one substance to the other. It doesn't matter whether they're 2 reactants, 2 products, or 1 of each. It does also assume that we have enough of our other substance for that reaction to occur completely. Now we can look at the product side and say to produce 4 moles of water, we would need 1 mole of propane, or C3H8, and 5 moles of oxygen. So these are the sum of the relationships we can get from our balanced chemical equation. We can get relationships between any 2 of our substances, regardless of which side of the arrow they fall on. So let's look at an example. How many moles of CO2 are formed when a half a mole of C3H8 is burned? So when we look at this relationship, we know that if we have 1 mole of C3H8, that we get 3 moles of CO2. We can actually set this up as a ratio by saying 1 mole of C3H8 over 3 moles of CO2, or if need be, we can invert this relationship to say 3 moles of CO2 to 1 mole of C3H8. Both of them give us the same information. It really depends on what information we're starting with to determine which version we're going to use. So here we're given a half a mole of C3H8, and we're asked to figure out how many moles of CO2 are formed. Because I have moles of C3H8 in the numerator, I know that I need that in the denominator for my relationship. So I have 1 mole of C3H8 and 3 moles of CO2. So when I do the calculation, I find that I have 1.5 moles of CO2 formed. In the next unit, we'll be approaching stoichiometry calculations, this time involving masses instead of just moles.